There are two contrasting types of social organization. One, our own, is based on learning. The other, represented by the bees, ants, wasps, and termites. In this film, you will see an example of a society in which individuals are directed in their activities by inherited behavior patterns, instinct.
Insects, as a group, vary tremendously. Their variations or adaptations, niches or ways of life. Among the most complex adaptations are those to be found in the social insects, termites, ants, certain wasps, and one of those interesting, the honeybee. The honeybee is a social insect. What do we mean by this? First of all, social insects are adapted to live in colonies. Second, each colony has castes, specialized groups of similar individuals. Third, each caste has particular adaptations, the result of millions of years of evolution that enable it to perform special functions, jobs that it alone can do and which are vital to the survival of the whole colony. Let's examine the three castes of the honeybee. First, the worker caste. The worker is a sterile female, a female which does not mature sexually. Hence, she does not mate and usually does not lay eggs. The queen is a fertile female. She may be the sole mother of a thriving colony of from 50 to 90,000 workers, but she usually mates only once, storing the sperm received from the male in a special receptacle. The male bee is called a drone. One writer has described him as lazy, stupid, fat, and greedy. There is, in fact, only one justification for his existence: to mate with the queen. Now, for the moment, let's consider one specific structural adaptation in the honeybee, the sting. The sting has evolved from the ovipositor or egg-laying apparatus. Consequently, only females have stings. The worker bee has a sting which is barbed, as you can see. The queen sting is not barbed, and the drone, being a male, has no sting. Why? What function does all this serve in the life of the colony? Let's see what happens when a worker uses its sting. The worker's sting, you remember, is barbed. It stays in the skin and tissue, and the worker bee dies when the end of her abdomen is torn loose. If a foreign insect invades the colony and is stung by a worker, both the worker bee and the invader die, but the colony as a whole is protected. You can see then that the survival of the colony is more important than the survival of the individual. After the individual has made its unique contribution to the welfare of the colony, it either dies or is eliminated by the others.
Here is a colony of bees in a commercial hive. Each of these frames contains hundreds of wax cells constructed by the workers. These are used as storage vaults for honey and pollen and as brood cells for the young bees. Here is the queen, marked for easy identification. Each hive contains only one queen, perhaps 50 to 100 drones, and 50 to 90,000 workers. The queen is constantly attended by workers who face her in a circle. They feed her, clean her, groom her. Thus, the queen depends on her attendants. If she produces eggs faster than honeycomb cells can be built, she is given less food. Her egg production slows down. Conversely, if she falls behind in her schedule, she is fed more intensively. Each egg is laid at the base of a cell. After 3 days, the egg hatches into a larva. Then, for 3 more days, each larva is fed a secretion from the salivary glands of the workers. This is called royal jelly. After the 3rd day, the worker larva is fed bee bread, a mixture of pollen and nectar. Larvae grow rapidly until they almost fill their cells. Then, worker bees cap the cells with wax, secreted from their wax glands. After 6 days, the larva spins a cocoon and gradually develops into a full-grown bee. This metamorphosis takes 12 days. The whole process from egg to worker bee has taken 21 days. Now, after 2 to 3 days, the worker sets to work. For about 2 weeks, the worker is a nurse bee. She builds the wax comb and tends the larvae. Here we see the wax flakes being removed from the wax glands in the bee's abdomen. The bee removes the flakes with the spurs of her middle legs and, transferring the wax to her jaws, manipulates it into the remarkably uniform 6-sided wax cells. For the next 10 days or so, the worker is engaged in household activities. She cleans the hive. Here, a dead pupa is being removed. She may help to air condition the hive. Workers fan cool air in from the outside. Young workers also guard the entrance. But at last, the young worker emerges from the hive to forage for nectar and pollen. Here we see bees collecting pollen on their hairy legs and body. The worker's legs, seen in close-up, are a remarkable set of tools for collecting pollen. On the fore and middle legs are fringes of short, stiff hairs. The worker bee uses these to brush the pollen from various parts of its body. Pollen combs on the inside of the hind legs concentrate the pollen, and it is then packed into the so-called pollen baskets on the outside of the hind legs. When the baskets are loaded until they bulge, the bee returns to the hive and deposits the pollen into special cells. Packed down and combined with nectar and other substances, it becomes bee bread. The transfer of pollen from one blossom to another is called cross-pollination. The pollen grains carried by the honeybee are brushed off, and the sperm nucleus within the pollen tube unites with the egg nucleus of the other blossom. Many fruit growers keep hives of bees, not for the honey they produce, but to pollinate the flowers of the fruit trees. In each locality, there come a few periods each year when nectar is brought to the hives in large amounts. These periods are known as honey flows. The worker bee sucks the nectar from the flower with her long tongue. The worker alone has an elongated tongue for this function, just as she alone has specially adapted legs for collecting pollen. Back in the hive, the nectar is regurgitated and deposited in a cell where it will ripen into honey.
Thus we have seen the worker bee perform a truly astonishing variety of jobs. But we come now to what is perhaps the most astonishing fact about the honeybee, behavior which seems, in the words of the German biologist Dr. Karl von Frisch, who first described it, too fantastic for belief. I am speaking about the honeybee's remarkable system of communication, the so-called dance of the scout bee.
A scout bee discovers a rich source of food in the field. On returning to the hive, she performs an amazing dance. When the food is in the immediate vicinity of the hive, the scout bee performs the round dance. During this dance, the bees near the dancer follow her, keeping their antennae close to her body. She turns around, once to the right, once to the left, repeating these circles again and again. This is the simplest dance performed by the honeybee. It communicates nothing about direction. It seems to say, simply, fly out and search for food near the hive. However, if the scout bee finds a source of food farther away from the hive, the dance performed communicates much more. This has been called the wagging dance. The scout runs a short distance in a straight line while wagging the abdomen rapidly from side to side. Then she makes a complete turn to the right, turns to the left, and then repeats this pattern over and over again. This dance indicates not only that there is a rich source of food far away from the hive, it also tells how far away and the direction. If the dancer heads directly upward on the vertical comb, this apparently means the direction of the food is towards the sun. If the straight run is down the comb, the direction is away from the sun. If the food is to the right of the sun at any angle, the direction is indicated by a run on the vertical comb at the appropriate angle from the vertical. The distance of the food supply is communicated by the number of turns in the dance in a given time. For example, at 300 yards, there are 9 to 10 complete cycles of the dance within 15 seconds. At 600 yards, there are about 7 complete cycles in 15 seconds. And once the dance is completed, workers issue from the hive and make a beeline for the spot.
Thus some details about the dance of the honeybee, one of the most remarkable mysteries of their complex social organization. But there's something else which is perhaps equally remarkable. For years, various scientists had observed this dance without understanding its meaning. In fact, von Frisch himself had observed it time and again, but had arrived at a wrong interpretation. Let me read you what he wrote when he at last discovered his error. It seems as though a happy dispensation from my scientific guiding star allowed me to discover this error myself. But let younger investigators be warned by this example, as they strive impatiently to publish their results after long years of frustration. Let them test their findings doubly and trebly before they regard any interpretation as certain. For often nature reaches her goal by another path where man cannot see his way.
With the coming of summer, the beehive becomes overpopulated. Soon thousands of workers will form a new colony with the queen. Before leaving the hive, however, the workers ensure the survival of the old colony. They tear apart and enlarge ordinary brood cells, building special structures, queen cells. The queen lays fertile eggs in each cell. The queen larva is fed only royal jelly. It is literally immersed in it. With this diet, the queen larva matures quickly, in only 16 days. But before the new queen emerges, the old queen and most of the older workers prepare to leave the hive. They gorge themselves on honey. Then they pour out in a dense swarm. If left alone, scout bees go out to find a new home. But at this stage, the commercial beekeeper captures the swarm. Carried to an empty hive, the bees move in quickly and set up housekeeping. Meanwhile, in the old hive, a fascinating drama is taking place. A new queen is emerging from her cell. Her first task, to kill off her rivals, those still helpless in their cells, and those which happen to emerge at about the same time. These two queens will fight to the death. The workers do not interfere. If both queens are in danger of being stung, they separate. One queen must survive, and one does. Now, the drones are vital members of the colony. They have been fed and housed all summer long, and now will earn their keep. Within 8 days, the virgin queen flies from the hive. Mating takes place on the wing. The drone dies. The queen returns to the hive, and in 2 or 3 days lays her first egg, the first of perhaps 2 million. As autumn comes, the honey flow diminishes, and the bees prepare for winter. There occurs now another amazing social phenomenon of the honeybee, population control. After the fertilization of the queen, the drones have been useless. They are relentlessly driven out or killed. When winter comes, bees, unlike some insects, do not hibernate. They remain active within the hive, forming a winter cluster, the heat of their bodies generating warmth. The bees in the center work their way out. Those on the outer edges work their way in. Thus the colony survives. During the long winter, the queen lays no eggs. But with the coming of spring, the complex social life of the colony will start once again.
Thus, we have seen some of the truly astonishing social activities of the honeybee. Many species of bees are not social, but there are other insects which have an even more elaborate social life than that of the honeybee. I have spent many years studying the social insects, particularly the termites. And I believe we can learn important lessons from a study of these insects if we carefully compare both the differences and the similarities of their social life with ours. Some social insects, for example, make war on other colonies of their own species, but this is not very common. Most of the warfare among social insects is between different species, not within the same species as we see it between tribes and nations of men. All social insects communicate. We've seen the remarkable system of communication of the honeybee. Human beings communicate information in various ways too, but there is a vast difference. The so-called language of the bee is instinctive and inherited, and has evolved slowly through millions of years of evolution. The individual bee does not have to learn the dance, nor do bees have to learn to respond to the dance. They react instinctively. We humans employ a much more complex and useful language, or I should say languages, which we must learn. We learn the knowledge of past generations, including language, from our parents and by going to school. Insects, of course, have no schools. They also have no science and no artistic creations. They have no morals or awareness of the beauty and mysteries of their environment. But on the other hand, they cooperate with others of their kind more smoothly, but it is true, with far less versatility than man. Perhaps, by discovering the reasons for such differences and similarities between our social life and the social lives of the insects, we can learn to improve our own societies and our